So this is the core math of edexcel A level, further math, the chapter 1, complex numbers. This is the solution for the mixed exercise with the flag questions. So I'll start with number 2. The equation has no real root, the range of possible values of b. So it doesn't have real roots, which means discriminant should be smaller than 0. So discriminant b squared minus 4ac smaller than 0. So this is like b minus 2 square root of 14, b plus 2 square root of 14. So this is like this. So when it is smaller than that, then b should be between 2 square root of 14, negative 2 square root of 14. Number 4, binomial expansion or otherwise show that this is the one. Okay, let's go for the binomial expansion. So this is the degree with 5. So 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. So 1, 5, 10, 10, 5, 1. So let me skip just the expression for 1. So let's do that with the 2i. So 2i start with 0. So 2i to the power of 0, 2i 1, 2i squared, 2i cube, 2i to the power of 4, 2i power of 5. So the first one is 1, second one 10i, negative 40, negative 80i, plus 1680, plus 32i. Therefore, the real part is 1 and negative 40 and 80, which is 41. And imaginary part is 10, 32, which is 42 minus 80, negative 8, minus 38i. Number 5, z squared minus 6z plus 10, the solution. We can use the quadratic formula for that. So to like negative b plus minus square root b squared minus 4ac over 2a. So 6 plus minus square root 36 minus 40 negative. So 6 plus minus, this is negative 4, which means 2i over 2. So the solution 3 plus minus i's are solutions. Therefore, 3 plus I is a solution to f of z equals 0. Number 8, this is the one, and find the z in the form. So 4 minus 7i over 3 plus I equals z. 3 minus I, 3 minus I. So the denominator is 3 squared minus I squared. And numerator 12 minus 21i minus 4i plus 7 minus 7i squared, which is plus 7. So 19 minus 25i over 10. So 19 over 10 minus 5 over 2i. Number 10. When z equals a plus bi, show that. So z over z conjugate. We will multiply by z on both sides because z times z conjugate always make the real number. So a minus bi times a plus bi and a plus bi squared. So the denominator is a squared minus bi squared, which is plus b squared. So a squared, only real part, plus bi squared means negative b squared, plus 2abi. So did you see it? Complex number is like this, and given the real part object is 1/13. So we cannot find any real part like this. So we need to find 3 plus qi over q minus 5i, q plus 5i, q plus 5i. So we want to know only real part. So the numerator is q squared minus 25 plus 25. So real part is 3q minus 5q. No, I mean, oh yeah. So 3q and minus 5q. So negative 2q over q squared plus 25 becomes 1/13. So negative 26q equals q squared plus 25. So q squared plus 26q minus 25. Oh, plus 25 equals 0. So possible values of q, like q plus 1, q plus 25 equals 0. Therefore, q equals negative 1 or q equals negative 25. Possible values of z in the form a plus bi. Yeah, you can, when you put it, there's no space here. So let me add. So possible values of z. Here, when q equals to negative 1, 3 minus I over minus 5i. So negative 1 plus 5i, negative 1 plus 5i. So 1 minus 25 plus 25. So negative 3 minus plus I plus 15i minus 5i squared. So 2 plus 16i over 26. So when q equals negative 25, 3 plus 25i over 25 minus 5i. So just to make the calculation easier, 5 minus I, so I'll multiply 5 plus I on both sides. 3 plus 25i. So 5 over 25 minus 1. So 15 plus 3i plus 125i minus 25. Negative 10 plus 128i. 5 times 26, which is 130. Yeah, you can simplify further, but I will skip it. Let's go for the next one, number 12. So the possible value of z, number 12. X plus iy, okay. So let z equals x plus iy. So x plus iy plus 4i x minus iy becomes, the real part is x plus negative 4y and negative 1, which is plus 4y. Plus imaginary part is y plus 4x. Therefore, x plus 4y becomes negative 3. 4x plus y becomes 18. So 4x plus 16y becomes negative 12. Then y, 15y becomes negative 30, y becomes negative 2. Y equals negative 2, then x equals 5. So therefore z, x and y, that's it. Number 14. Z is like this, and ZA plus BI, AB rational given that in the form in terms of Q. Okay, so this is actually, we don't understand this form, so we need to make denominator with just real numbers only. So Q plus 3I over 4 plus QI, 4 minus QI, 4 minus QI. So the denominator is 16 plus q squared. And the real part is 4q plus 3q. Imaginary part is 12 minus q squared. Therefore, 16 plus q squared, 7q plus I. 16 plus q squared, 12 minus q squared. And the next one. Six minus 2i is one of the roots of quadratic equation with real coefficient. Real coefficient is explaining that if we, like conjugate root theorem, if it has 6 minus 2i as a solution, then without solving it, we know that 6 plus 2i is also the other roots. So that's why it says write down. So find the quadratic equation. Okay, so when z equals 6 minus 2i, it's an easy way to find this quadratic formula. Anyway, z is 6 minus 2i, so we want to find the quadratic formula who satisfies z as a 6 minus 2i. So z, we start from z equals to, like z equate z and 6 minus 2i. So z minus 6 becomes negative 2i, so we square them. Because we don't want to continue to have the imaginary numbers on our expression, like equations, so we isolate the I and square them after that. So z squared minus 12z plus 36 becomes negative 4. So z squared minus 12z plus 40 equals 0. And number 16. If 4 minus ki is a root, then we know 4 plus ki also a root because this is real constant. So this one is like z minus 4 equals negative ki, z squared minus 8z plus 16 equals negative k squared. Z squared minus 8z plus 16 plus k squared becomes 0. K squared should be 36. Therefore, k equals 6 because it should be positive. And m equals 4 because 2m should be 8. Number 17. 2 minus I is the root, then 2 plus I is the root. So we solve the question. I'm not sure whether we learned about the sum of the roots of the polynomials. So actually the sum of roots always like negative a n minus 1 over a n, which means that this is the leading coefficient here, 1. And this is the 1 degree lower coefficient, which is z squared. That's the coefficient of z squared, which is 0. So this is the sum of roots. So we have 2 plus I and 2 minus I, and we don't know what it is. Let's call it P. It should be 0. So P equals negative 4. So we found all roots now. Therefore, z equals 2 plus I, or z equals 2 minus I, or z equals negative 4. Number 18, again, same. So this also, again, the roots are, some of the roots are 0, but just we are not sure about it. So we just follow the way of the textbook explains. So 1 plus 3i is the root. So z equals 1 plus 3i. We will find the quadratic factors. Z minus 1 becomes 3i. Z squared minus 2z plus 1 becomes negative 9. Z squared minus 2z plus 10 becomes 0. So z squared minus 2z plus 10, and we don't know what it is. Let's call the other root as a p. This should be z cubed plus 6z plus 20, which means the constant is only negative 10p and 20. This should become 20. So p equals negative 2. So again, we know all the roots. Z equals 1 plus 3i, z equals 1 minus 3i, and z equals negative 2. Number 19, 4i is the root. Then find the k. So 4i is the root, then negative 4i is the root, and we don't know what it is. Let's call it p again. So, but the number a is asking us to plug in 4i into z. Because the next question is about the other solutions. So 64 negative I plus 48 negative 48 plus 4ki plus 48 equals 0. So now we don't have any real part. Only we have imaginary part, and it should be 0. Therefore, k equals 16. So other two roots of the equation, we have 4i and negative 4i and p again. So z equals 4i, z squared becomes negative 16. So z squared plus 16 and z minus p should be z cubed 3z squared plus 16z plus 48. Therefore, p equals negative 3. And number 20. This has the form of like two quadratic factors. Actually, we have more. I mean, we can go further for this. But anyway, here it asks us to be like this. So let's compare the coefficients. So it's very easy to see c equals 10 because the only constant term is negative 60, should be negative 6c. And for the the z3, like determine z cube, should be negative 1. And here like this and like this, negative 5 plus b. Therefore, b equals 4. So all the solutions to be found, like z squared minus 5z minus 6, and z squared plus 4z plus 10 equals 0. So the first one, we can factorize it, so it's not very difficult to find it. Oh, sorry. It's so ridiculous. So here, z minus 6, z plus 1. So z becomes 6, or z becomes negative 1, or z becomes negative 2 plus minus square root I square root 6. You will find it as you apply the quadratic formulas. Number 21. 3 minus 2i, then we have 3 plus 2i. So 3 minus 2i, 3 plus 2i. So let's find the other quadratic factor again. So I will give you another solution rather than the making squares. So this one, when we know the two solutions for the quadratic solutions, you can compose the quadratic equation like z squared minus sum of z, not of, sum times z plus product equals 0. So when we add them together, this is 6. So z squared minus 6z plus product z 9 plus 14. No, I mean 9 plus 4, 13 equals 0. So we can tell how this happens. 3 minus 2i, z minus 3 plus 2i. So for the term of z, like this and like this, so we need to add them together for the sum. And the constant term, both of them, which is product of them. So this is the one. So now find all solutions. Oh, still, where is it? So number 21. So just now we found one of the quadratic vector, z squared minus 6z plus 13, and z squared plus az plus b, let's say, which b is 6 because of 78. Or actually you can make the long division. It's all up to you. Nothing is so difficult here. So the cube term is like negative 6 plus a should be negative 6. Oh, so a is not there. So this is the factorized form like this. So we will find the solutions like 3 minus 2i, 3 plus 2i, plus or minus square root of 6i. Number 22, 4 equals 0. So now we can find the p. When we put 4 there, 4 to the power of 4 minus 4 to the power of 3, 5, 4 squared, 4p plus 24 becomes 0. So this one, 64 times 2, 128 minus 80, 48, so 72, negative 18. So x, not x, like let's reduce the degree. 1, negative 2, negative 5, negative 18, 24. 4, 2, 12, negative 24. So now we have x z to the power of 3 plus 2z squared plus 3z minus 6. What do we have further? Yeah, we have another like 1. So this is the factor theorem. Just now when I put 1, I could make a 0. So 1, 1, 3, 3, 6, 6, 0. So z minus 4, z minus 1, z squared plus 3z plus 6 becomes 0. Z equals 4, z equals 1, z equals negative 3 plus minus square root 9 minus 24, negative 15, I 15 over 2. So the solution is 4, 1, and negative 3 plus I squared to 15 over 2, negative 3 minus I squared to 15 over 2. Let's do the challenge. Why a cubic equation with real coefficients cannot have a repeated non-real roots? If it has repeated non-real root, which is like twice a plus bi, a plus bi, and a minus bi, let's say, we cannot make the sum as a real number because the coefficients of the polynomials, they represent the sum of the roots and product of roots and something like that. So we need to make the roots, like a sum of roots, as a real number. By means of an example, the quartic equation with real coefficient can have a repeated non-real roots. Let's say I, negative I, negative I, for example. So z squared plus 1 squared. This is quartic equation who has the non-real root repeated.